right, let's go ahead and take a look at your homework from last night. If you're watching on YouTube, I realized after recording the test instructions, which I was in no frame of mind to remember to give you homework apparently, I realized, oh, I failed to give homework, so I went ahead and gave it to these students. They have done it. If you have not, look in the description of the previous video for that homework assignment, or actually I just say it now, you're supposed to read pages 326 to 329, and then on page 339, answer questions 1 through 8. They have done it. If you have not, pause the video, get the assignment completed, and then resume. Let's go take a look at the questions. Question number 1 says, what is the term for a sudden release of accumulated electric charge? Michael, what'd you have?
The sudden release of an electric charge is called a discharge.
Very good. We think of it as a zap, but discharge is the technical term. Number 2, what is one evidence that 2 types of charge exist, and what are the 2 types of charge called, Audrey?
One evidence that 2 types of charge exist is the law of electric charges, and then 2 types of charge are positive and negative.
Okay, that's good. I think the book was looking for a little bit longer answer, actually talking about the pith balls and how they could attract or repel and different charges that way. But yeah, they are positive and negative charges. We'll talk about those. For sake of time, number 3, list the name and charge of an atom that has an excess of electrons and a deficiency of electrons. Kendall.
An anion has an excess of electrons, which becomes negative, and a cation has a loss of electrons, which becomes positive.
Excellent job. Number 4, what are the charge carriers for current in air? Michael.
Atoms carry the charge for current in air.
Primarily, yeah, ions and some free electrons if there's a big enough charge buildup, but typically the ions carry the current. Good. How about number 5, what are charge carriers for current in a liquid? Audrey.
The charge carriers for current in a liquid are cations and anions.
Good. When in a liquid is just going to be ions, you're not going to get nearly as many free electrons. Number 6, what are conductors, insulators, and semiconductors? Kendall.
Conductors are the transmitters of a current. Insulators are not the transmitters of current, and semiconductors, therefore, transmissions of current.
Okay, good. Conductors, good carriers of current. Insulators, they don't carry current. And semiconductors, poorly carry current. Number 7, what carries charge in a solid conductor? Michael.
Electrons carry charge in a solid conductor.
Specifically, do you give one more word, maybe an adjective on electrons? How about you, Kendall? Call them delocalized electrons. We'll talk about those here in a little bit. And number 8, what are the 4 best solid conductors? We'll go back to Michael.
The 4 best solid conductors are silver, copper, gold, and aluminum.
All right, there we go. All right, silver, copper, gold, aluminum. In your notes, next section, static electricity. Static electricity. We're skipping over chapter 21 for sake of time. Some interesting things in there that you can look through with wave optics and diffraction patterns, but really not a lot in there as far as what I would want to test you on, and we are running short on days. And so I need to take every opportunity I can to get to what I consider to be some more critical concepts. And there are some things that I remember when I was in high school and even in college struggling with. I want to help you with those things. We're working towards circuits in a little bit, which was something, again, I struggled with that I feel like I've really been able to help students understand in years past. So we're going to skip some stuff. But we need to understand basic electricity. And we start with static electricity. Your definition for static electricity. Electric charge that builds up in an object. Static electricity is electric charge that builds up in an object. Electric charge that builds up in an object caused by, caused by a gain or loss of electrons. Static electricity is electric charge that builds up in an object caused by a gain or loss of electrons. That term, by the way, electron, the book mentions, comes from the Greek word electron, E-L-E-K-T-R-O-N. It's the Greek word for amber, the tree sap stuff that just seemed to attract lint and stuff to it. And so they referred to this charge, these electrons, as electrons from that term. And so we understand, and we're familiar with static electricity, right? We've all been zapped touching a doorknob or maybe touching a chalk tray or something like that. We're familiar with this idea of static electricity. Static electricity comes as your body oftentimes adds extra electrons to it, right? Especially if you're wearing shoes with a rubber sole to them, and maybe you walk across some nice thick carpet. Now, You might have noticed here at school, the static electricity doesn't tend to be super bad. We've got very thin carpet. Where I went to college, there was in the library, they had really thick, plush carpets there at PCC. And the nice thing about those carpets, of course, it absorbed lots of sound, right? Didn't reflect sound off, so if you were quietly talking to someone else in the library, your conversation didn't echo throughout the entire building. And they also, though, kept the humidity really, really low in the library because the books get damaged by humidity. So they ran the air conditioning. It was always a little colder in there, not very much humidity. And so between those two factors, your shoes could pick up the electrons as you walk. You don't necessarily just step, step, step. There has to be some kind of friction. We talked about that action-reaction. You've got to slide your foot backwards somewhat for the ground to push you forward. And so as your foot slides, it just took a few electrons off that thick carpet, and they accumulated on your body. And your body just added more and more electrons until you reached for that door handle. And I tell you, there was no worse place on campus, Michael, than the library stair tower. When you reach for that handle, and zap, okay? You got shocked by that release of accumulated charge. That term is discharge. It was in a homework question. Discharge is the sudden release of accumulated charge. Discharge is the sudden release of accumulated charge. We understand this, right? Everything tends toward neutrality. Everything tends toward equilibrium, so to speak, if we want to think of this as electrical equilibrium. So if you've got a buildup of charge on you, this buildup of charge is looking for a place to go that doesn't have the same buildup of charge. And that door handle presents a ready opportunity. Or if you were to shake somebody else's hand. Now, if somebody else has been walking on the same carpet, and you were to shake somebody's hand, you've both been on the same carpet, and you both have an accumulation of charge. Is that an opportunity for the charge to release to the other person? Not if you have the same charge as each other, right? But if there's that difference in charges, maybe somebody just stepped through the stair tower doors. They have not yet walked across thick carpet like you have. Then you could zap them instead. But that door, again, everything tends toward neutrality. The door can just drop all of its electrons down into the ground. So you reach for that door, and the tip of your middle finger approaching the door is just a nice pointy object to zap. And that's why you felt that discharge. Now, in theory, if you were to stand around long enough and just stand there, little by little, the free electrons would dissipate into the air. You get bombarded by air molecules constantly, right? Eventually, molecules, as they bombard you, would grab one of the electrons and go. You'd get some charged ions as a result, but it's going to take a long time because, again, everything tends toward neutrality. Why would air molecules don't naturally just grab electrons and go, right? So it could eventually grab electrons little by little. That discharge could take place, but it wouldn't be a discharge now. It's what we call dissipation. Dissipation, D-I-S-S-I-P-A-T-I-O-N. Dissipation is a gradual release of accumulated charge. And if you didn't have a class to get to right away, or you had nothing better to do with your time than just stand there next to the doorway, waiting for the charge to slowly leak off of you into the air, so to speak, dissipation, that gradual release of charge, then maybe you could avoid getting your hand shocked. Or what else you could do was wait for some other sucker to touch the doorknob first and then walk through the already opened door. That's a great strategy also. Another thing I discovered you could do, and if you did it slowly, it looked really weird, but you could walk to the door, bump it with your arm, which allowed a wider discharge. The discharge covered a wider area. Instead of all the current flowing through one finger point, it was flowing over a larger area. So you didn't feel much of a shock. Bump the door, that released the charge, and then open the door. Again, if you did it slowly, bump, open. You look like a doofus, but you just walk up naturally, bump the door open, and nobody's really paying attention. Play it off as cool. But things you got to do to survive. The PCC, Rebecca Horton Library. But anyway, I don't know how it would be at other college libraries, but that's how it was at PCC Library. Now, there are three charges. I say three charges. Neutral is not a charge technically, but it is a state if we want to think of it that way. Neutral refers to having no charge. A total balance of positive and negative. Again, neutral is what everything tries to attain, that electrical equilibrium, if you want to think of it that way. However, you could obtain, as we talked about even in chemistry last year and years past, a positive charge. This would be if electrons were somehow removed from your person. Most Van de Graaff generators actually strip electrons and produce a positive charge on the dome. Some, depending on the way the rollers are positioned, produce a negative charge. I believe this one produces a positive charge. But a positive charge just means a deficiency of electrons. One of the ways that a deficiency of electrons could be produced, and you may have seen this before, is to take a glass rod. Glass gives up its electrons fairly easily, and silk can strip off electrons. And so if you rub the silk on the glass rod, you can kind of hear it popping right now. That's producing a positive charge. Now, it's also producing a little heat because of friction. The friction doesn't actually produce the electrons. It's simply the two substances rubbing against each other. Again, you're hearing that popping sound, and you can see that it responds to things, right, by producing that positive charge. Now, the opposite charge would be a negative charge. A negative charge is produced by an excess of electrons. A negative charge is produced by an excess of electrons. Usually, this is more what we think of when we think of a buildup of charge. Right, for instance, you all did this when you were in physical science with Miss Morse, right? You rub the balloon on your head, and the idea is the rubbery latex, really, of the balloon strips electrons off of your hair. Things like hair, carpeting, bunny rabbit fur. PETA people just unsubscribed. I did not have anything to do with the decease of the bunny. I'm sure it was humanely disposed of. Anyway, but the bunny rabbit fur. I think this is real fur. I'm not sure. It might be fake fur. But anyway, has the same effect, for instance, as rubber shoes, rubber-soled shoes across thick carpet, right? The fur supplies electrons. The rubber picks up the electrons from the fur. I'm not hearing this sparking sound or that sound. Let's see if we can get it to respond. A little bit of a response here, right? Where it produces, and you can see the little hairs are sticking to it here. I do have some little pieces of tissue. I'm sure you've done things like this before as well, right? You've taken the little pieces of tissue, or you can even do this with a stream of water from the faucet. You can do this with a candle flame as well, producing the ionization in the plasma. But you can attract little pieces of tissue, kind of like we attracted the yarn. We see the pieces responding to this charge. Now, why would something, because again, assuming the tissue is neutral, right? Why would the neutral tissue attract to a charged body? Well, remember, neutral means within the object, everything's in balance, right? Positive, negative is in balance. But it doesn't necessarily mean that positive, negative is evenly distributed, right? As I took the negative rod and put it close, we know first, we'll write this down, we know it already, so I'm talking as if we've discussed it. I haven't actually had you write any notes. The law of electric charges. The law of electric charges states that like charges repel and opposite charges attract. The law of electric charges states that like charges repel and opposite charges attract. You knew that already, even if I hadn't gone into it, but for the sake of making sure it's in the notes, because you will be tested on it. So making sure that we know it. Like charges repel, opposite charges attract. Let's go with the glass rod now. As I put the glass rod close to these pieces of tissue paper, even though the tissue paper is neutral, what is the positive rod doing? It's causing within the tissue paper, one side of it, you see how the tissue paper stands up. The negative in the tissue paper, the electrons in the tissue paper, run upwards toward the positive. They're attracted by the positive. Positive charge is driven away. As a result, these are more or less what we call polarized, where one side of the tissue is one thing and the other side is the other thing. Now we've got a chain of tissue forming here where negative, positive, negative, positive, negative, positive attracted down this way. Again, the tissue paper was neutral, but it attracted because it sort of polarized, so to speak. We could do this as well with the Van de Graaff generator. Again, we've got electrons will be taken away from the dome little bits at a time by the belt as it's moving. And we'll see what happens here with these pieces of yarn. Again, off camera, we'll have see if the ladies are wanting to do this with their own hair. We've got yarn hair here. But we see that if indeed the sphere is charged positively, then there's a lack of electrons all over these little pieces of yarn, correct? Which means they're seeking for electrons. Well, the other pieces of yarn don't have electrons for them, do they? So they're also going to repel from each other. This, however, has electrons in it. It's neutral, right? There's no charge on this. This has electrons these are seeking. So we're going to see that these attract to the rod in search of electrons. Oh, you create a little bit of a loop there. Do we see how all the pieces respond? Now, if I give this a positive charge, right? That was already positive. It sucked whatever electrons were available off. This now has a positive charge. Now nobody wants anything to do with this, right? We see them going away from each other. Until I come over to Michael. I didn't actually touch Michael, it was his book. Now it's neutral again. I was able to release the charge here. And so once again, they're attracted to what could be a source of electrons for them. Does that make sense? Okay. Now, what we see here is a lot of charge. Again, this has the electrons that we need. By the way, make sure you don't have electronics near something like this here in a minute. So if you're wearing a smartwatch, you'll take that off. But we've got a buildup of charge here, a buildup of positive charge, seeking negative. This has some negative to supply, but the problem is even there's a gap. There's a gulf fixed, so to speak, between this little guy. This is kind of interesting here. So remember I talked about dissipation, a gradual release of charge. This one's heavy, so it's gradually releasing a little bit more quickly. Its sheer weight is losing. But you see they're staying charged for a little bit. There aren't a lot of just free electrons in the air waiting to be given up. Molecules have electrons, atoms have electrons, but if they give up their electrons to this, then they become charged. Everything tends toward neutrality. So it's going to hold that charge until some sort of discharge is released. And then they'll fall back down into place. Now, at this point, they're almost attracting the other stuff. So as I touch them, I'm taking off whatever charge is there. And as soon as I give them the charge again, as they accumulate more and more positive charge, you can also see the little hairs on them. Now, hey, this is kind of fun to play. You see why I was playing with this so much last night. It's just fun to play with these little guys. And this thing evidently has what kind of charge right now? It's repelling. It must have a positive charge. There's not extra electrons it wants. It's nothing doing to my hand has it, so it's kind of chasing after my hand here. But it doesn't want anything to do with this. And now they all love it. Oh, no, they got too much of the positive charge. So anyway, but the air tends to insulate, right? The air tends to block electrons from freely flowing. But if you get a big enough buildup of charge, difference between, in fact, let me do this. Okay, you guys. Can you see it traveling through the air? Well, the little hairs are getting in the way here. But you see the sparks forming in the air. If there's a big enough charge difference that forms, then you can get the discharge of free electrons to leak through the air, and that produces a spark. We're going to let this discharge a little bit, or dissipate a little bit. But this flow of charge, right? This had charge. It released charge, positive charge, so to speak, by taking electrons from me. That discharge that you saw, of course, you see as that spark. I'm not sure if the camera could see it. Could you all see the sparks flying? All right? It didn't hurt too bad on the back of my hand. Again, flatter surface is not as bad. It's great to get hair standing on end, that kind of thing. It's a weird feeling, too. Have y'all got to do that before in physical science? You have?
Well,
Think so. If not, we'll do it after class off video. But anyway, I was doing it after school one time, playing around with this thing, and it was right after PE. So I'm in shorts. My leg hairs were standing straight out. It's the weirdest feeling and the weirdest looking thing too. You're just glad you weren't there. But anyway, this flow of charge from one place to another is referred to as current, if you'll jot that term down. Current is the flow of charge. Now, within a within any object, you have atoms, and atoms themselves become charged. We had these terms earlier, but write them down in your notes if you would. Anions, remember, are ions that are negatively charged. They have gained electrons. Ions are negatively charged. They have gained electrons. We see most of these have fallen down at this point. So the discharge is slowly happening. The air around here kind of feels funny still. Like you can still see this thing responding, even though it appears to have lost most of its charge. Anions, negatively charged atoms that have gained electrons. Cations from the homework again, positively charged atoms that have lost electrons. But through air, it is actually ions largely that carry the current. Cations, anions, these charged atoms that are created in the air that carry the current. But again, the air doesn't tend to naturally carry current. Air in general, make sure you jot this down, is generally an insulator. Air is typically an insulator, meaning it stops the flow of charge from one place to another. Air is generally an insulator that stops the flow of charge from one place to another. Again, if you're looking at this, you can still see those yarn strips have charge in them. One piece is still standing up. All the pieces are standing outward a little bit, and it's been a few minutes now since I turned that thing off. They're holding on to that charge as much as they can. Little by little, the air will take the charge away. But air is generally an insulator. However, if you get a big enough charge difference, right? I am relatively neutral. That thing is rather charged up. Get a big charge difference, you can get that discharge. In air, then, you can get a spark because you're trying to pass current through an insulator. So when a big charge difference is formed, it will produce a spark only in air. You won't get sparks in solids or liquids, but you can in air. Again, you can get some free electrons to move as well, but largely through air, it's the flow of ions. In liquids, well, liquids aren't generally insulators. Liquids allow charge to flow easily because there's so many atoms, right? So many molecules moving around. Where around us, air is a lot thinner, right? The molecules are spread out more. They're moving very quickly, but they're more spread out. So the chances of a molecule rushing by and grabbing an electron is minimal. In a liquid, although they're free to move, the atoms are much more tightly packed in a liquid, right? We understand that. And so, therefore, the ions are formed more easily. If there's any free electrons, they'll grab them and go. And so ions flow easily in a liquid. Because it's so easy for current to flow through liquids, you do not get a spark in a liquid. All right, so because ions move so easily through a liquid, you typically will not get sparks through liquids. Current flows very easily. This is one of the reasons probably when you were a little kid, you had a safety class or something where you talked about if you see a downed power line, stay away from it. If there's a downed power line in a puddle, don't go anywhere near the puddle. Don't use corded power tools in the rain, because if your extension cord has a little cut in it that you didn't know about, it can charge the puddle, and then you step in the puddle, you get electrocuted. Y'all remember learning those things when you were younger? Okay? And again, it's just because liquid so easily carries current from one place to another. Hair dryers at the bathroom sink, right? Mom's told you, if you use hair dryers, mom's told you to be careful of that cord. Again, I'd hate for there to be just the slightest little cut in that cord that I didn't know about. It gets down to that sink, and then somehow you touch that water, and all that current goes flowing right through your body. So want to be very careful with that. But what about in solids? Right, in liquids and gases, the atoms, the molecules, they move on their own. So if you've got ions, ions can move from one place to another. In liquid, atoms are free to move, molecules free to move. If they happen to have ions, they just move from one place to another, trying to attain neutrality, right? Going to a place where there's less negative charge. What about in a solid? They can't do that, can it? Atoms and molecules have fixed positions. They vibrate in place, but they have fixed positions. Well, some of the substances on the periodic table have a lot of electrons. Some of those electrons are actually free to leave what we call the parent atom. They can go from one to the other. You talked about covalent bonding and sharing electrons, but you could also just lose electrons to another atom nearby. These are called delocalized electrons. And you need to know that in solids, because atoms can't move, delocalized electrons carry charge. Delocalized electrons are what will carry the charge. In a solid, delocalized electrons carry the charge. Now, delocalized, we all know what local means, right? Local means from around here, right? You ever met somebody and you could tell from the accent that they weren't from around here, you know? You know, you're not a local here, right? You were born in Michigan, right? So you're not technically a local, though you've lived here most of your life. You're a local. Born, bred, raised, Georgia, this part of Georgia. You're very much local. St. Francis, okay, so very much a local. I'm from Indiana originally, grew up in Florida, moved here 13 years ago. Okay, so I'm not a local. That which is local stays put. We would say you're a local girl, you're a local boy, you've stayed put, okay? That which is not local ain't from around here. Delocalized electrons don't stay put. They move from one atom to the next, to the next, to the next, to the next. And it makes sense, does it not, that substances on the periodic table that have more delocalized electrons would be able to carry more current more easily, right? If there's only a couple of free electrons that are able to leave, that's not going to carry a whole lot of charge. Furthermore, they're going to bump into other electrons that are stuck orbiting and buzzing around the parent atom. Those kind of get in the way. That also slows down the charge. More delocalized electrons, better carrier of current. And so substances with a large number of delocalized electrons are called conductors. Conductors. Substances that carry current well because of a high number of or high percentage, you almost might say, high number of delocalized electrons. Conductors. Good carriers of current because of a high number of delocalized electrons. Well, what are some of your conductors? Well, in general, metals, right, are very good conductors. In general, metals have a high number of delocalized electrons. The four best metals, in order of their number of delocalized electrons, and therefore their electrical conductivity, are silver, just put Ag because it's easier, copper, Cu, gold, Au, and aluminum, Al. Quick review of periodic table from last year, right? Silver, copper, gold, and aluminum. Now, question for you though. If silver is the best conductor, then why don't we use silver wiring in our buildings if it's such a great conductor? Way too expensive, right? Silver's far too expensive, so of course we don't use that. That's why most of the wiring in buildings is copper. It's the second best. Now, it's also somewhat pricey, but nothing like silver, so copper is usually used in wall circuitry. Gold, yeah, even more so, right? It's not even the best. Copper's better than gold. Why would we use gold when it's so expensive? Aluminum's interesting. Aluminum's a pretty good conductor, and it's much cheaper than copper. Wall circuitry can't use aluminum wire, okay? It needs more current than is able to flow through that. But have you ever looked at a small appliance, maybe a lamp or something, and seen the wiring? Usually, or oftentimes in small things like lamps or light fixtures, maybe some fans, you'll get aluminum wiring. Again, it's cheaper, still a decent conductor, not as good as copper, but if you're not passing a lot of current through, you might use aluminum. What about things that don't have any delocalized electrons? For instance, rubber, wood, plastic. Now again, there's electrons on the surface. They can strip electrons off. Like, you ever slid down a slide at a play place, maybe when you were younger or maybe last week, and you slid down the slide and when you got to the bottom, your hair was standing on end? Okay, I have small children, so I enjoy watching Chloe, who has this really thin, light blonde hair, and it'll stand out when she's going down the slides at Burger King Play Place, for instance. Well, what's happening is that plastic is taking electrons off of her clothing, right? The clothing supplies the electrons to the plastic, and the plastic just ends up getting coated in electrons, and so she now has a charge. And so when she runs in and says, "Daddy," and she goes to give me a hug, zap! And then she looks at me like I hurt her. It's your fault, kid. Now, when I go down the slide, chasing after her, and I happen to try, then it's my fault. So, yeah, I don't like getting shocked, so I don't like going down the slides at Burger King. Also, the slides are very high up. These are like monster slides these days. Have you seen the slides at Burger King? It's like a sheer drop. And I'm like, at my age, I don't sheer drop too well. So anyway, I usually let the kids play now. But anyway, insulators are substances that do not have delocalized electrons. These are what we wrap the wires in, okay? This is what we wrap the wiring or sheath the wiring in so it keeps the electrons where they belong. Insulators do not have delocalized electrons and therefore current does not flow through them. When I was in a health class and we talked about health and safety and electrocution and stuff, I still remember my ninth grade health teacher giving us a tip. If you saw somebody, like maybe they stuck their finger in an outlet, or they, somehow were touching a wire, a bare wire that was in an outlet, and they were getting electrocuted, and he used to say, beat them with a broom. Now, not actually like beat them with a broom, but knock their hand away with a broom handle, because broom handles are usually made of either wood or plastic. Neither of those conduct the charge. You can't grab them. Their body is mostly water. Water carries charge very well. So suddenly, both of you are being electrocuted, so knock their hand away from whatever's zapping them with a broom handle. Beat them with a broom. I still remember that. Thank you, Ken Kramer, for that. And he's a school administrator now in Tennessee. Anyway, beats people with brooms. Anyway, there are some substances that have some delocalized electrons, not a whole lot, so they carry a little bit of current. These are called semiconductors. Semiconductors. Probably heard a lot about those here in recent days, perhaps. Semiconductors, really high in technology these days, because think about it. Do we want a lot of current flowing through your phone? No, just a little bit of current, just enough to run all the circuitry, right? In your computer, just enough to run all the circuitry, right? So we don't want full-on conductors in there necessarily. We want semiconductors. Silicon is one you've probably heard of a lot. Silicon wafers used in microchips and things like that. So silicon and germanium are the two big ones that are used today. Silicon and germanium. Silicon Valley has kind of become synonymous with the tech industry. So silicon and germanium are two prominent semiconductors. They're for uses when you want just a little bit of current to flow. You actually want to force the current not to be too great through a device. And again, intricate circuitry in computers or phones, technology, it's usually where that is used. A lot of what we talked about today, I think, is review from physical science and chemistry. I don't think I've taught you a lot of new stuff today. Are there any questions on what we've talked about? All right, well, we will end the video here so that we can let students play with the Van de Graaff generator. Homework for this evening, though, before I forget like I did yesterday. Homework for this evening is to read pages 329 to 333. Read pages 329 to 333. And on page 340, answer questions 9 through 14. Page 340, questions 9 through 14. All right, we'll take a look at all of that in our next lesson. If one of our students isn't with us tomorrow, we'll know something went terribly wrong with the Van de Graaff. Just kidding, it's safe. I won't have you doing it to teenagers. Have a great day.